Now let's explore an example to understand the power of principal component analysis when we work on high dimensional data. And of course, PCA principal component analysis is one of the dimensionality reduction methods. Let's take this example. So PCA for portfolio optimization and risk management. So in finance, PCA can be used for portfolio optimization and risk management by identifying uncorrelated principal components representing different asset classes. Okay. So let's begin with our first step, which is import libraries. So what are libraries we are going to import? Let's do that. So as usual, let's import pandas. Pandas as PD, NumPy as NP, and from SQL Learn library decomposition package and PCA module, and from SQL Learn library pre-processing package import standard scalar module for standardization. These are the things we are gonna import. Okay. Then let's pre-process the data. So but before pre-process the data, let's go through the data story. So for that we have to load the data. So here I'm gonna load the data set, and my data set has been loaded using read underscore CSV function from the pandas library, and I have given the respective address of the data set. Okay, so now let me execute and see what is our data set consists of. Okay, so let's get into the story. Let's have a data story for the portfolio data set that contains various financial metrics for different companies. So let's begin with the company name. What you see is the first column is company name. The data set includes the names of various companies listed in the stock market. Then what we have here is a stock price. So stock price is a critical metric that represents the current trading price of a company's stock in the market. It indicates the market's perception of the company's value and performance. Then what we have is a market capitalization. So market capitalization is the total value of a company's outstanding share shares of a stock. It's calculated by multiplying the stock price by the number of outstanding shares. So this is also called as a market cap. So market cap reflects the overall size and valuation of the company. Okay, then what we have here is EPS, another very important parameter. So EPS, earnings per share. So EPS is a measure of a company's profitability. It represents the portion of a company's profit allocated to each outstanding share of a common stock. Higher EPS values indicate higher profitability on a per share basis. So this is our EPS. Then we will move on to the price to earning ratio, P by E. This is also another important aspect, a parameter. Price to earning ratio is a valuation metric that compares a company's stock price to its earnings per share. It helps it helps investors assess how much they are paying for each dollar of earnings. A higher P by E ratio may suggest that investors have higher expectations for the company's future growth. Next, very important parameter of stock market data is a dividend yield. A dividend yield is the percentage of a company's annual dividend payment relative to its stock price. It indicates the income generated from dividends for each rupee invested in the stock. So that's what is called dividend yield. So then what we have here is beta. So beta is a measure of company stock price volatility. So compared to the overall market, a beta greater than 1 indicates the stock is more volatile than the market, while a beta less than 1 suggests lower volatility. Here you can see 0.53, which is lower volatile, and the beta, which is greater than 1, basically indicates the greater like higher volatility than market. Okay, then let's move on to the debt to equity ratio. Here it is. The debt to equity ratio measures a company's financial leverage and indicates the proportion of debt financing compared to equity. Higher ratio may indicate higher financial risk. So this data set provides a valuable financial metrics for various companies, allowing investors and analysis to gain insights into their financial health and performance. Okay, so these are the information regarding that. So by using this data set and conducting further analysis, investors can make informed decisions on portfolio construction, stock selection, and risk management. So that's what we will be using this data set and to perform PCA for the dimensionality reduction. Let's get back to the next step. So now it's time to move on to the step 3. Okay, it's time to do pre-processing on text data. So let's standardize the original data to have zero mean and unit variance. How can we do that? We can do z-score standardization or z standardization or normal standard normal distribution method way. So let's do that. So let's import the standard scalar. Then of course these are my features. Let me check stock price, market capitalization, earnings per share, EPS, price to earnings ratio, P by E ratio, dividend yield, beta, debt to equity ratio. Debt to equity ratio, these are my features. Now it's time to standardize this features to have a zero mean and unit variance. How will we do that? So again, we have to instantiate standard scalar class object, and here is this is what we call it. This scalar is the variable name for the respective instance. Okay, instance. Let's take this scalar now. I want to standardize the complete features data, so that's the reason. So I'm using the scalar object, and then I'm calling up a method called fit underscore transform method, and I'm gonna give the respective features. So with this, the whole data will be standardized. If you want to see that, I'm gonna show it to you. So scaled data, scaled data, and here it is. So it's a complete array, and it's got standardized. How it got standardized? It got standardized with the zero mean and unit variance, zero mean and unit variance, and that's what had happened here. So now there is not much of there are no features which has a higher magnitude, but before, if you see here, the market cap is very big. It would be around billions and multi-billions, okay, whereas your stock price is just of hundreds, and your beta is 1.18, and dividend yield is 0.01, and EPS is 2.08. So this one has very high magnitude, so this is going to influence a lot than compared to the other ones. So that's the reason it's we have to bring it down all to the same magnitudes or same levels or of same scale, and that's what we did here, a standardization, and that's the pretty important step in dimensionality reduction method and of PCA, specifically PCA. Okay, so that's it. This is what is the second step. Now it's time to move on to the third step. So let's calculate the covariance matrix of the standardized data. It's time to calculate the covariance matrix of the standardized data using NumPy covariance function. Let's do that. So covariance underscore matrix, it's a reference variable name, and NP is our library, and from that covariance, the cov function has been called up, and then obviously you have to give the scaled data, and row variance, let's keep it false, and let's execute and see. Cov matrix, and this is what we got. This is our covariance matrix for all the features. Of course, here, let me see, covariance matrix, and if you want to get some information regarding n dimensions, it's 2 dimensions, and size, it is 49, of course, and shape, sorry, it's 7 by 7. Okay, exactly as we have discussed earlier. How many features we have? Our features 1, 2, 3, 4, 5, 6, 7, and our covariance matrix is 7 by 7. Okay, 7 by 7, exactly 7 by 7 covariance matrix has been calculated as we have discussed earlier. As we have 7 features, so first variance covariance would be between stock to market capitalization, then stock to earning per share, stock to P by E, stock to dividend yield, stock to beta, stock to debt equity ratio. In the second row, market to stock, market to EPS, market to price, market to dividend, market to beta, market to debt, and same will be repeated. So what you get at the end of the day as a covariance matrix is a 7 by 7 that you can clearly see on your screen. Now let's move ahead. Next, it's time for eigenvectors and eigenvalues. So let's let's compute the eigenvectors and eigenvalues of the covariance matrix using a linear alg module from NumPy and EIG function. Okay, let's do that. So eigenvalues, eigenvectors from NumPy, I am calling up a linear algebra. From linear alg, I'll be calling up eigen, and I'm gonna give covariance matrix, and let's see the respective values. So eigenvalues, sorry, let's call up the eigenvectors because those are the directions, and these are the eigenvectors. Of course, how many eigenvectors we have? Let me check. And its 2 dimensions are 2. Okay, that's fine. And let me go for the shape. Of course, we'll have a 7 by 7. We have 7 vectors. Okay, So now out of these seven vectors, of course, size would be 49. Out of these seven vectors, how many eigenvalues will have, that you should correct. We got the seven eigenvalues, that's it. Because so each vector you take it as a matrix, and each matrix will have an eigenvalue, and seven matrices or seven vectors will have a seven eigenvalues. And this is vector 1, vector 2, vector 3, vector 4, and vector 7. So total we got the seven eigenvalues for the seven vectors. And that's up. Now let's move ahead to the step 5. So now it's time to, once you compute the eigenvectors and eigenvalues of the matrix, then we have to sort the eigenvectors based on their corresponding eigenvalues in descending order. That is very important. Very, very important. So that's what I'm going to do here. Next step is to sort the eigenvectors based on their corresponding eigenvalues in the descending order. So obviously I will use the index technique. So this, I'll put it to -1 here so that I can get into descending order. So let me use sorted eigenvectors just to see. And this is the order of sorted eigenvectors. Okay, now it's time to choose the principal components. So choose the top k eigenvectors or principal components that capture the desired amount of variance. Let's So I have to, for this example, I have taken k is equal to 2. I want top 2, the number of principal components I want to choose. I want only 2 principal components. So then we will filter them out using indexing concept. So choose the top k eigenvectors that capture the desired amount of variance, and k is equal to 2. So those are the number of principal components I want to choose, and selected eigenvectors is equal to sorted underscore eigenvectors. So let's execute and see. Selected eigenvectors, and out of them, so these are the overall eigenvectors. Okay, so sorted out of this, these are the sorted eigenvectors, and out of that the selected eigenvectors. Now let's move into the next step. So now it's time to select the principal components. So it's pretty project the original data onto the selected principal components to obtain the reduced dimensional representation. So once this eigenvectors has been selected, now it's time to reduce the data. So project the original data. This is our original data. Then this has been standardized, and then covariance matrix, eigenvalues, eigenvectors, a lot of things were done. Now it's time to project the original data onto the selected principal components. How do we do that? Using this. We have to use a dot product. So np dot. So to do that, selected scaled data and selected eigenvectors. So we are basically projecting the original data into the selected principal components. So then let's create a new data frame for the reduced dimensional representation. That's pretty straightforward, and I want to check principal component 1 and principal component 2. Then finally, let's print the selected features, and that's what the final step. Let's do that. So display the first few records of the reduced data frame, and let's execute. And here is your diamond here PCA, which has given you the output, the company names, and of course this is just uh, it's just a top five. You have the company names, and then in spite of this parameters, this what you got was just components, a principal component 1 and principal component 2. That's it. So if you just want to print the complete tf underscore reduced, and here it is, the complete 1567 rows and 3 columns with the principal component 1 and principal component 2 and applicable to the all companies data. And this is what you got. This is what we call it as a dimensionality reduction using PCA. So here what we have done is manually. So most of the things we have calculated using NumPy library methods. But this time we will use a directly PCA library to do the same, so that the things would be much easier. So load the data, and standardizing remains same using standard scalar. Okay, we will be standardizing data all features and instantiating the standard scalar class object, then call up the fit underscore transform method from the scalar object, and then the data should be given is your features. Then the most important step, if you use a library, you have to instantiate a PCA class object, and you have to give a reference variable name. That could be anything. Here I have given PCA, small p, small c, small a. Then that's it. You have to fit the data respective scaled data. Very important. The scaled data has to be fit. So I have called up the fit underscore transform method from PCA, and I have given a scaled data as an argument to it. And that's it. Now you can, if you want to calculate the explained variance for each component, you can just call up the explained variance ratio from the PCA object. It's just an attribute. Explained underscore variance underscore ratio is just an attribute, and you just call up that attribute from the PCA object, and what you got is this. And it had made 8, let me execute this. Yeah, we got the 7 components. So out of 7 components, the explained variance of principal components, component 1, because we got the 7 variables, and 7 variables were converted into the 7 components, which are, of course, we cannot tell what is what exactly, but that's fine. This is component 1, which is the component 1 is nothing but your stock price. Okay, so the component 1 got, let me execute. Yeah, here it is. The component 1 got 0.1565 variance, and component 2 0.1494 explained variance, and component 3 0.1456, component 4 0.1416. Of course, these 4 got very no higher amount of variance, whereas the others have slightly lesser than that, but that's fine. This is how we calculate the explained variance of the principal components of the respective data set. So then once we have calculated the explained variance, now it's pretty straightforward. Let's select the components from that. We have to retain top 4 components. That's what my target. So I want to take n components, which is top 4, and selected components is, of course, my principal components, and out of that I'm going to filter out n components, which are 4, and let me execute it and see. So selected components, and these are my selected components which are standardized. If you want to see an shape, and here it is, you got the 4. You see that the 4 components. What's next? Then it's time to print that. Okay, then it's simple, straightforward. You have to create a new data frame for the reduced dimensional representation. That's it, and then display the first few records of it. And let me execute it and see. And this is our reduced data set. And here the company name, because this we see it as a target variable, and then a remaining features. These are my features, and these features has been reduced down from 7 to 4, and which has a higher variance and a higher explained variance, basically explained variance, higher explained variance. So at this is how we can use the dimensionality reduction method to reduce your dimensions, and we have reduced the dimensions from 7 to 4.